I took the MCAT January 16th of this year, so not too long ago, only a couple months. I scored a 520 with my score breakdown shown below. Okay. All right. So, so for today, like you saw, we're going to be talking about mainly force and kinematics with a little bit of work in there. So our learning objectives for today are the important kinematics equations, the three Newton's laws, solving force problems, what is work and how it is used, and what torque and other advanced force topics are. Because force and energy and work are huge topics in physics, we won't be covering all of it in depth today because it's just not possible in an hour and a half, 2 hours. But for the extent of the MCAT, in terms of mechanics, mechanical forces and kinematics, we'll be covering most of that. There will also be separate lectures for different electromagnetic forces, electrostatic forces, and all of that. So that's a separate lecture. But for most of the basics, we'll be covering today. Okay. Now let's move on to the content. Okay. First day, I want to start off with kinematics. And if you took a college level physics class, this is likely the first or second lecture you went over. It's the very basics of physics. So in kinematics, there are really three main quantities that it focuses on. There's distance/position, which is usually labeled as x. There's velocity, which is usually v, and acceleration, which is usually a. So these are all very closely related through the following equations. So velocity equals change in distance or change in position over time. And acceleration is change in velocity over time. And the d, lowercase d, just means change because it's a derivative, but you don't really have to know any calculus. But generally, velocity equals change in position over time, and acceleration equals change in velocity over time. Okay. Note when we're using these formulas, calculating over a set of time, so over say 10 seconds, they're usually the average velocities and accelerations, which is we'll get to later, but it's a very important distinction from instantaneous velocity or instantaneous acceleration in the moment. So for example, say you moved 20 feet in 2 seconds. Using this equation, we would find that your average speed or average velocity would be 10 feet per second. But that doesn't necessarily mean at all points you're moving at 10 feet per second. At some point in time, you're probably moving 8, some point in time, you're moving 12, and so on and so forth. But the average from what we can see is 10 feet per second, okay? And the same thing applies to acceleration and velocity. If you have if you're going at 60 miles per hour over like a certain time, we can find the average acceleration. If you went from 0 to 60 in say 30 seconds, we can find the average acceleration, but we wouldn't really know the exact acceleration at every point. Okay, and that's a very important distinction. Another thing I wanted to mention, and sometimes people get confused with this, with acceleration specifically, is an acceleration of 0 does not mean that the object is at rest or the object isn't moving. An acceleration of 0 means that the object is not speeding up or slowing down. For example, something could be going through the air at 10 meters per second at a constant rate of 10 meters per second, right? Its acceleration would still be 0 meters per second squared, but it would still be moving and it would have a velocity. Velocity of 0 means that an object is at rest. It means the object is not moving, okay? So there's two main equations that we want to look at when figuring out kinematics, and that is these two. You've probably seen these before in your physics class. As I mentioned, x is position or distance, if you want to think of it that way, but in this case, it's position. V is velocity, A is acceleration, and T is time. You see there's an x0. X0 just means the initial position, whereas x represents the final position. Vi implies the initial velocity, whereas just v implies final velocity. Okay. And so the main use of these equations is in solving problems. Most of the problems you'll see on the MCAT relating to kinematics will be solved with these two equations. There are other kinematics equations, but usually they're derived from these two equations, okay? And if we look at the equations, we can actually make sense based on the units, right? So we know that position has units of meters and distance has units of meters. Velocity, as I'm sure many of you know, has units of meters per second. Time has units of seconds. Acceleration has units of meters per second squared. So meters equals meters plus meters per second times seconds. That's again makes meters plus 1/2 meters per second squared times second squared, which just again makes meters. And all of the units add up, right? And again, if you want to even think about it, just in real life, physics is one of the topics that's more intuitive to you because you have followed physics your entire life, right? You understand physics at some level without even taking the course. So you're sorry, could you please everybody could you please mute unless you have a question, okay? Thank you. And I'll stop after this slide to ask for questions, okay? So if you want to think about it just in terms of real life, your final position is just where you started plus how fast you were going over the time it took you to go there, plus how fast you were speeding up or slowing down times the time squared, okay? And with this one, again, very simple. Your final velocity is just your initial velocity plus however much you're accelerating or decelerating in the case that it's negative or slowing down. Okay. Okay, like I said, I'll stop here for questions. Please put them in the chat. And while I'm lecturing, you can always ask questions in the chat. We'll answer those. Yeah, so please, yes, again, please mute your mics unless you have a question. If you have any questions, please put them in the chat or raise your hand or speak up. Well, I won't be there. I won't be there on the MCAT to tell you when to use equation. So I don't know what you mean by that. Usually, like when you would use equation is when you would have enough information, right? If you're looking at positions, you would use this first equation because it has position x and x0. Whereas if you just have velocity and acceleration, you may be looking at this bottom equation, right? And with this equation, the top one, usually it's more for like projectile motion. So if you say you threw like a rock somewhere and you wanted to see how far away it would go or how long it would take until it hits the ground, you would usually use this equation, yes. Where this equation is usually not used on its own. The second one, it's usually not used on its own. Much more likely you'll be using it in complementation with this first equation. So, you know, sometimes you may have two variables. Well, what do you do if you have two variables? You need two equations, right? So sometimes you may be using both the equations together to kind of two equations, two variables to help solve the problem, okay? All right. So let me see any other questions. Yeah, we will have practice problems in this lecture. There'll be more towards the end and there'll be more for the more complicated topics, okay? But we will have practice questions. We have polling open that we can use, okay? These equations you do have to memorize. Some equations they give you, but these are ones you have to memorize because they're considered fundamental physics equations, okay? I will be using my pen to write on the slides, but if need be, but right now, where's the V final equation? So this is the V final equation, the second one. So this V, if it doesn't have a subscript, it's like current V. It's not V final, it's current V. The v final equation is it's also derived from these equations. So you can memorize it, but you can essentially get it from these two equations. You don't need to. Yeah. Yeah, and Chris put it in the chat. Chris is one of the other tutors as well. He put it in the chat. It can be useful. Like I said, you can really you can kind of like figure it out on your own, that equation. These are just the fundamental ones. That's why I'm focusing these. Yeah. Okay. Okay. Any other questions? Any questions? Okay. And feel free to ask. I'll always go back. Okay. So now I want to talk about the application of these equations. Okay. So the most common application of these formulas and this topic in general is follow questions. So like I mentioned, you throw a rock and it's going in the air at an arc. How far will it go? How much time will it take until it hits the ground? Questions like that. Maybe something like that. Anything like that involves like throwing, falling, anything like that. Okay. So when we talk about free fall or any type of projectile motion or any falling, we really want to focus in 2 dimensions, right? And because there's an x dimension, so that this way, like me going forward, backwards, or if you want to think about it on a 2D plane, going this way, okay, left to right, and a y direction, so up and down, okay? We want to kind of split it into 2 different parts, right? So for any falling object, we always know the acceleration in the y direction, right? It's always negative 9.8 meters per second squared, because that's the acceleration due to gravity on Earth, at least, right? We always know the acceleration, so that's, if I go back to the equations, so this a, we always know this in the y direction, right? So if we split this formula only in the y direction, going top and bottom, we always know this a, okay? All right. So the acceleration, velocity, and distance traveled in the x direction and y direction, like I mentioned, is completely unrelated to each other for the most part. The only thing that ties them together is the time. When something hits the ground, obviously when you throw something and it hits the ground, that's its final time. That's how long it was in the air for. When that happens, obviously in the y direction, x direction, it stops moving because it came to rest. Okay. So therefore, like I mentioned, when asked a kinematics question in 2 dimensions, I recommend that you split it into 2 parts, an only x direction and an only y direction, right? So say we're using this first equation, which is the most common one. We want to do position, final position, initial velocity, and acceleration in the x direction only, and then final position, initial velocity, and acceleration in the y direction only. Say if you were to, like I mentioned again, throw a rock a certain distance, right? Well, they would usually give you the initial velocity. And now let's look at it in both directions. In the x direction, usually they would give you the initial velocity. You know that the initial position is 0 because it's all relative. And you want to make yourself, where you're throwing it from, 0. So initially started at x position of 0. X final is usually what you're trying to find, or sometimes it's t, depending on the question. X final is just where the rock landed. T is the time it took to reach that point. And acceleration, usually in a problem, acceleration in the x direction is 0 unless otherwise stated, because there's nothing going against you, right? If you throw a ball in the x direction, at least, it won't speed up or slow down. In real life, it does slow down because of air resistance, but in this level of physics, we ignore air resistance, so the acceleration is usually constant, which is 0. Okay, so we take this equation out in the x direction, at least. We usually take this out. This they give you. This is usually 0, and this is usually what you're trying to find, either x or t, depending on what they give you again. Now we want to look at this same thing in the y direction. Again, x, and this time x final is usually 0 because in terms of height, usually things come to rest when they hit the ground. The ground is usually a position of 0. Okay, So in the y direction, the final position is usually 0. The x initial is in the y direction is usually where you threw it from, the height. So say if your arm is 4 feet in the air, it's usually 4 feet or something like that. Vi is usually, we don't know this. This is usually something they either give you or you have to figure out. T is again something you would have to figure out, and we know A is always negative 9.8 meters per second squared. Okay, so that's how you do it. You'd split it up, maybe find if you're looking for the T. So if they ask you how far does a rock go, in the x direction, how far does it go when it hits the ground, right? You'd find, say, the T using this y direction equation in the y direction. If you would have all the variables, you just solve for T, you'd find out what T is, and then you would plug it into this exact same equation except in the x direction, and you would find out what x final is. Okay. Any questions on that? I know it was maybe a little bit confusing, but does anybody have any questions on that? If not, then I'll move on. Okay. All right. All right. So now we'll be moving on to force. So that's where the bulk of this lecture will really be about, force and work. The kinematics was just really an introduction. Yeah, we will have examples of everything in the end. Okay. And if not, I'm sure you can always find examples online. It's very easy. But we will have a couple of examples, just of general questions you may see later on. Okay. And these force problems will also take into account your knowledge of kinematics. So what we just talked about will come back again for the rest of the lecture, okay? But now we want to talk about Newton's 3 laws, okay? You all probably know Newton. He pretty much, I guess, discovered gravity. Some people say it made a lot of like what we know in terms of force, equations, and acceleration, everything like that, okay? And he discovered these 3 laws, which we still haven't found an exception to them, okay? So his first law was that an object at rest will remain at rest unless acted upon by a force. An object in motion will remain in motion unless acted upon by a force. I'm sure you all know this. So if you have, say, a box, unless some kind of force acts on the box will not move. If you take the box and you throw it or you slide it, it won't stop unless something acts against it, okay? This may be a little bit counterintuitive to what you can see. So if you take like a box, obviously it'll stop eventually, and if you slide it, but that's because a force does act against it, the force of friction, okay? So you slide the box and then force of friction acts against it and the box stops. And we'll cover that much more in detail in a bit. The second law is the force applied to an object correlates to the object's acceleration. So this is the classic equation F equals ma, where F is force, m is mass, and a is acceleration, as we mentioned earlier. Right? This is the equation. This is the basic equation that we'll be using for all of our forces, essentially, and it's kind of the fundamental equation for force. And this tells you a lot. So the speed, the acceleration with which something moves, so again, speeding up or slowing down, is directly tied to its force. So if you apply a weak force on something, then it'll accelerate a little bit. If you apply a stronger force, it'll accelerate a lot more, right? And the third law is that every action has an equal but opposite reaction. When you apply a force to an object, the object also applies a force onto you. Okay. Now, this is all a little bit abstract. How do we actually use this? Okay. So there are many different types of forces that we'll encounter. So some of the most common and most basic are the normal force and weight. Weight is what essentially we think of as gravity, and it's what pulls you down to the ground. It's what keeps you from floating away. Weight is equal to mg, where g is the acceleration due to gravity, as we mentioned earlier. It's equal to 9.8 meters per second squared. Okay, and again, weight is a force, and it's equal to mg. If we look at this exact equation again, F equals ma, well, we have weight of force is equal to m times g, which is an acceleration. So this follows very simple law. The normal force is the force applied onto an object by a surface that holds it. So again, every action has an equal but opposite reaction. When I apply force to the floor applies a force onto me to hold me up. Otherwise, I would sink through, right? And this is what we call the normal force. So the normal force, unlike weight, has no set formula. It is simply the force opposing other forces. So in this case, it opposes weight. So it is also equal to mg, okay? Right, and if you look at this diagram, so there's gravity or weight pulling us down with a magnitude of mg, and then you have the normal force is the ground pushing us up by an equal but opposite amount of also mg, okay? This is not, especially with the normal force, this is not always the case. It's just an opposing force that is applied from the ground onto anything that holds it, or any surface onto whatever it is holding. Okay, and I'm sure much of this is reviewed. Okay, one common thing that you will often be seen doing is breaking forces into components. So if you've learned about this in physics, forces are vectors. They have a direction, right? A scalar is something that has a magnitude. Like for example, speed. Speed might be a good scalar because you can be moving at 10 meters per second, and that's it. Whereas velocity is a vector. You move 10 meters per second, but where? In what direction are you moving? Okay. Well, same thing with force. And somebody asked in the chat, the PowerPoint and the recording will be posted. Yeah, the PowerPoint will be posted. But yeah, forces are vectors. So this means that they have a direction. Sometimes this direction is not convenient for us to work with, right? What we can do is we can actually break this vector into components. Okay, so in order to effectively make a force diagram, which is how we solve all force problems, we must set our axes. So typically, we set our axes based on the plane of an object, right? Because of this, we must sometimes break the forces into components to make it easier. And I'll show you in the next slide how that works. So we have this object, and this is just the zoomed in version of this picture, right? It's on an inclined plane, okay? And we have two axes. So you can see this axis going this way and this one going this way. We essentially set our axes, so we could make it any way we want. We could make the axes like this and make it a perfect cross. But that's not very convenient for us to work with. The thing that's most convenient for us to work with is doing it in the plane of the object, essentially. So the object is slanted this way, so we want to make axes like this, okay? When a force is in an axis, so like you see this Fn, the normal force, is exactly in the plane of the axes, it's perfectly fine as is, nothing to worry about. But sometimes not all forces are in line with the axes. So like you see this weight is going down, but it's actually not on one of the axes. The way we fix this is we have to break weight into components. And this is where I will begin annotating, okay? So we can break this line down into two components. So we can do an arrow like this and an arrow like this. Essentially, when you add up these two dotted arrows together, you get this weight, right? But notice how these two dotted arrows are in the axes. This one is in this axis, and this one is in this axis, right? So now they're very comfortable for us to work with. Well, how do we do this? Well, how do we break something into components? Well, we have to use angles, and we have to use some trigonometry. If you notice, this is a right triangle right here. This is a right triangle. Since we know that we know this angle, we also know this angle and this angle, right? This angle is just this, and this angle is what's left, right? And again, we broke down the components over here just so it's easier to see, but we could also break the components down like this, and it's easier to see as well. Okay. And this corresponds to the sides of this right triangle, right? This is the y component, and this is the x component, okay? So if you notice that we mentioned that in order for something to be accelerating, it has to have a force applied to it. That's what F equals ma signifies. This block, pretending this block was not accelerating in this direction, right? In this direction, this axis, right? If it's not accelerating in this direction, that means it has no net force in this direction. So that means this Fn and this component cancel each other out completely and give a net force of 0 because it's not accelerating in this direction. But it may be accelerating in this direction, right? In this axis. And that's likely what the case is because we have this component, this vector component, going along that axis in the left, towards the left, but we don't have anything canceling out going to the right. So likely this object, this thing on a ramp, is accelerating this way. How do we find out what the value of the components is? Well, we use simple trigonometry. We know what the value of the hypotenuse is, this long side, because it's weight and it's usually given to us. Mg is given to us. And we know what the angle is, because that's also usually given to us, or maybe it might be the unknown that you're trying to solve for, either way. And we know that, and we know this angle, and we know that sine of this angle is equal to opposite over hypotenuse. This is the hypotenuse. This is the opposite we're looking for, so we'll call this x because it's a variable, so we'll just call it x, and it's equal to sine alpha or theta or whatever this angle is, right? And this is how you do it. And if we want to solve x, it's just mg sine alpha is equal to this x component. If we have this component, we'll call it y. That opposes the normal force. Well, it's just mg cosine alpha. Okay. Does that make sense? Does anybody have any questions? Please put in the chat or raise your hand or speak up if you have any questions. Okay, so if no questions, we'll continue, and you can always come back and ask more questions in the chat if you'd like to. Okay, so we talked about two forces, the normal force, Fn, and the weight, Fw. What are the other different types of forces? Well, the next most common is the force of friction. The force of friction has the formula F equals mu times normal force. So friction always opposes movement and prevents sliding. Like I mentioned earlier, if you take a box and you just slide it on the floor, eventually it'll come to a stop. Normally this would violate Newton's first law, but it doesn't because there's a force of friction that acts against the box. It's the floor acting against the box, and it's going in the opposite direction to prevent it from sliding further. Okay. So there's two types of friction. There's kinetic friction and there's static friction. Kinetic friction is the friction when you're moving an object that is already moving. Static friction is the friction when moving an object that's at rest. And one way you can remember this is that static friction is always greater than kinetic friction. It's always more difficult to move something that's at rest than it is to move something that's already moving. Why is that? That's because the static friction is much higher than the kinetic friction. So the force that's opposing you when you're trying to move something is higher when when the object you're moving isn't already moving. Okay. And if we want to go back to our picture, if you were to draw how the force friction would look, the force of friction always prevents sliding, right? Well, we already decided that overall, this box is moving this way, right? Because gravity, it's moving this way. Well, if it's moving this way on a surface, the force of friction will be opposing that, and the force of friction will be this way, like that. And it depends. If the force of friction is exactly equal to this force that we already determined, then the object will not move at all. They'll perfectly cancel out, and the object will have no acceleration. I shouldn't say not moving, it should have no acceleration, right? It could be moving at a constant speed. If the force of friction is greater, which will never happen because friction can't be greater than something like that. So it'll actually won't go this way. But if the friction is less than gravity, then it'll just keep going this way and keep accelerating that way, I should say. Okay.
Quick question, Mark. In the the previous example, did you use how did you determine that the angle was alpha? Between the W and the arrow, the blue arrow. Were you using
so that's something you just have to kind of know. It involves trigonometry. I believe it's called, I don't remember what the principle was called. It was
similar. I think it's similar angles.
Yes. So, but just something you have to remember, like when it's like this, and if you're drawn like this, when you do enough of these problems, you'll kind of like memorize it, and you don't have to do it like that. I'm echoing Kajia, thank you. And just this one is alpha, and then you know that this one is just opposite of alpha because it's a right angle, right? That is just something you pick up when you're doing enough of these problems, right?
Fair enough. Thank you.
Yeah, if you go more into like geometry and trigonometry, then you'll probably like remember exactly what the principle was called. But the MCAT really is not testing on trigonometry, so
yeah, I think it's like similar angles or something like that. Yeah, it sounds familiar.
Yeah. Okay. So that's
Mark, I have another question following that.
Yeah, please.
So we're finding the value for X. So what exactly we're finding the magnitude of? I was just trying to figure out what you were solving for. Because was that angle given?
Right.
That theta,
right.
like we're assuming theta is, or alpha is something.
Right. Yeah. So because it depends on the question, but the general formula is that's an alpha. Just pretend that's an alpha. Sine alpha equals X over mg. Right. This is what I drew before. X is this component. Right. So what they may give you is they may give you alpha, they may give you mg, they may give you different things. They may ask you to find X, they may ask you to find alpha. I don't know what the question is going to ask you, but this is the general formula, and you just have to fill in what you already know. Sorry. So they may give you alpha, and you know that this is alpha, right? If this angle is alpha.
Yeah, I got that part. But what is X?
X is this component of, you see how this vector is not in line with the axes. This is the axes that we set. It's not on the axes, so we can't actually use it. But we can break it down into two components that are each on a different axis. So this, I'm going to draw it over here. If you have an arrow like this, you can break it down into a downward arrow and a rightward arrow. And when you combine these two dotted arrows, the product or the result will be this one arrow, right? So we can do the opposite. We can break down one arrow into two arrows. So we broke down this one blue arrow, the weight, into this arrow going down and this arrow going left, right? Because these two arrows, you see how this arrow is on this axis and this arrow would be on this axis. So they're actually on the axis, and we can use the two arrows, but we can't use the one arrow. So we want to break it down into two arrows. In order to find what this one arrow is, if you want to look at this graph as like a right triangle, look, this is a right triangle. This side of the right triangle, this one right here, that I'm keep highlighting, that's what this rightward arrow is actually equivalent to, right? And we know laws of right triangles from trigonometry. So therefore, if we find out what the value of this arrow, of this side of this triangle is, we know what the magnitude of this arrow is, this force vector. Does that make sense?
Yes, thank you.
No problem. Any other questions? Okay. Let me clear the annotation, sorry. Okay. So let's move on to other forces that we could possibly have. So we just talked about friction. Well, the other forces are tension and spring force. So tension is a force that is always present when there is a string or a rope involved. Spring force is a force that is always present, as the name suggests, when there's a spring involved, right? So if we pretend, so before we had friction opposing gravity in this thing, where friction was pushing it to the right. So if the overall movement of this block is this way, now pretend the slope is ice. It has like very low friction. Friction can't oppose this. But now you have, say, a string. So pretend this line is like a string hooked onto here, right? We can use a string to oppose this movement downwards. So in strings, the force caused by strings is called tension. And tension also opposes movement. So if you want to think about it this way, if the string is tethered to a wall or to somebody holding it essentially, and the block is going this way, the string will actually end up pulling the block back up because it doesn't want to move like from its tether point. So it actually ends up pushing pulling the block up in this direction. So tension would be going in this direction in this case. It would oppose this movement, right? And it's just tension is just the force caused by this string. Okay, and we'll get more into that in a bit. The other option is if you had a string. So again, a spring, I should say. So and springs, there could be a spring here. So this is a spring. And gravity is pushing it towards a spring. So you guys know how springs work. They stay in one position in the rest form, and then they would like to stay in that rest form. If you compress a string, it'll bounce back to its original position. Same thing here. You apply a force down to compress the string or the spring. The spring will apply a force to oppose it to make it go back to its original, to make the spring go back to its original position. In this case, if the spring is this way, it'll be applying a force this way in order to go back to its original position to stop itself from being compressed. This would be the spring force. If, on the other hand, you were to do something very similar to the string, where you would tether a spring on this side, well, the spring would be elongated, and it doesn't want to be elongated. It wants to go back to its original position. And that, so what it would do is it would try and snap back, and it would apply force in this direction to kind of go back to its original position, right? The key with springs is they always want to go back to their original position, and they always apply a force towards their initial position. Whether if it's compressing, it goes outward. If it's elongating, it's going inward. And I actually have a string right here, a spring. So if I try and, this is its initial position right here. If I try and elongate it, it gets harder and harder because the spring is applying a force in this direction to counter my elongation, and then it just springs back, right? Does that make sense?
Yes, quick question, Mark. You could go back to that diagram you just had.
Yeah, sorry, and we did put in the chat Hooke's law. It's right here. Yeah, I was gonna get to it in a second, but yeah, Hooke's law is F equals kx. But yeah, go ahead. Sorry, I cut you off.
Yeah, my question is, Opal, real quick, can you mute one of your computers or one of your tablets?
I did. I muted the computer.
Like also turn like the volume completely
Oh,
off
the
of
volume
it.
down. Okay, that makes sense. Okay, so Mark, you did say third law says force up equals force down, like the normal force is going to negate the weight. So why do you have that arrow going off, the blue arrow going off to the side? Shouldn't it be going straight down?
No, okay. So what I said was weight, no matter what you do, no matter what position you're in, no matter what, gravity always points directly down. No matter what, it always points directly down, because that's just how gravity works. It always goes straight down. The normal force doesn't always go straight up. The normal force always goes up from the surface. So if the surface is slanted like this, the normal force would go up from the surface, and it would actually go right here, right? So the normal force doesn't oppose gravity. It comes from a surface, and it always pushes off the surface, okay? Since gravity is always pointing down, but it's not on the axes, we have to break it down into components. Yeah, as Janelle mentioned in the chat, normal force is always perpendicular to the surface, whereas gravity is always pointing directly downwards. But downwards is not always the direction we set our axes. So in this case, we set our axes along like this, not along gravity.
Thank you. Makes sense.
Okay. Any other questions, or should I move on? Okay. All right. So I was talking about tension and spring force. So like I mentioned, tension is somewhat similar to the normal force. It also doesn't really have a specific formula. There are formulas that you can find online, but usually tension, especially how they give it to you on the MCAT, is more a force that you have to figure out based on like opposing factors, right? So they may give you something hanging on a string, and you know that the object is not accelerating, so you know the net force is 0. If you know the net force is 0 and you know the force of gravity, you'll be able to find out what the tension is, right? Because it opposes gravity and acceleration is 0, right? Otherwise, it could be given to you in the problem. Spring force does have a formula, and it's the same formula that was put in the chat earlier, Hooke's law, where the force of spring is equal to kx. K is the spring constant. There's not a set value for the spring constant. It depends from spring to spring. Each spring has its own spring constant, and they'll give that to you. Or they may ask you to find that. X is the distance of the spring currently from its natural position. Like I mentioned, if you have this spring, this is its natural position. Right now, it's expanded. So whatever its distance is right now, subtracted from the distance it is right here, the difference in distances is what X would be. So the more you expand, like I mentioned, the more you expand a string, the harder and harder it gets to pull, because the force is getting bigger and bigger of the spring force getting bigger and bigger, right? And any questions on this before we move on to our first clicker question? Or our first poll question? Yes, tension. So tension is always a force on a string or a rope, right? Or any kind of like pulley, right? So how you figure out the formula? So usually there's not really a formula for tension. It's more you have to kind of see it, and I'll give you a question I think later on where we talk about where we ask you to find tension, right? So yeah, for example, if they give you a very, very simple situation where they have a string with like a box hanging on a string, right? You know that the force of gravity on the box is always going down, directly down, and the tension is going directly up. They're in direct opposition. If you are told that the box is not accelerating up or down, you know what the net force is 0. If you know what the force of gravity is, you know that the force of tension is exactly the same as gravity, just in the opposite direction. Because of that, you can then just equate tension to mg, and you can find out what the tension is, similar to how we did the normal force, actually, right? K constant it's the spring constant, and it depends on each spring. So if you want to, sorry, if you want to think about it like kind of like the elasticity or whatever of the spring itself, but they'll always give you what K is. It's just what the specific constant for the specific spring they're giving you is. So I don't know what the K constant of this spring is, but whatever it is, it's just what it is for this spring, and a different spring would have a different K constant. Yeah, okay. And they may ask you to find what the spring constant is for a spring if they give you the force of the spring and the distance, the x. So it's very simple. Yeah, it'd just be, yeah, it's essentially the stiffness or elasticity. All right, so I'm gonna start this poll. If you guys wanna give it a try. Okay, so it was actually a two-way tie between A and C for the right answers. Okay. 43% said A, 43% said C, and then 4% said B, and 9% said D. The correct answer is actually A. And I'm glad that you guys narrowed it at least down to A or C, because as you know, they asked what the acceleration of the toy was. And if you look at the units, you can already eliminate B and D, because these are in newtons. So that was easy. Now all you have to do is just find what the acceleration actually is. Okay, so we know that the weight of this, or the mass of this, I should say, weight is different from mass. Mass is 2 kilograms. So I don't know if I stressed this yet, but the first step to solving any force problem is always make a force diagram. So using all the known forces, we know that gravity always downward, mg, normal force always upward, and in this case also mg, because it's directly opposing. Actually, I shouldn't say that. Clear. Yeah. Sorry about that. Gravity going down. There is a normal force. So we'll just call it Fn for now, along the ground with an applied force of 10 newtons. So we know that there's a force this way of 10 newtons. And a frictional force of 1 Newton. And we know that if he's sliding it to the left, friction always opposes motion. So friction is going to the right, and it's F of 1 Newton. Okay. And ask what is the acceleration? So To find acceleration, you just have to kind of break it down into components and find the net force. You find the net force especially in this axis. And once you do that, you can use F equals MA, right? So first thing we have to do is we have to break this down into components, and that's what the angle is for. What we're trying to find is this spot. We'll just call this X, this component, right? And we know that when we have this angle, we know this is the hypotenuse. So we know that cosine 60 is equal to X over the hypotenuse, which is this one, which we know is 10. And you do have to memorize that cosine of 60 is 1/2, and that sine of 30 is 1/2. So 1/2 equals X over 10, and you know that X equals 5. So it's a force of 5 newtons to the left. The only force in that other force in this axes, this left and right axes, is friction, which is 1 newton in the opposite direction. So you subtract, it's 1 newton. So 5 newtons minus 1 newton, and you get a total of 4 newtons equals M, which we know is 2 kilograms, times A, which is also 2, because 4 divided by 2 is equal to 2, and A is the correct answer. Does that make sense? Does that make sense to everybody? It's very, very straightforward, very simple. The only difficulty that I would see in this question would be if you would be getting tripped up with the angles, the 60 degrees. Remember SOHCAHTOA, 60, this one is adjacent. So you're looking for the adjacent, right? Because it's adjacent to this is the hypotenuse. So use cosine. And you know that cosine of 60, you have to memorize cosine of 60 is equal to 1/2. So 1/2 equals adjacent over hypotenuse, which you already know, and you can solve from there. Any questions? Okay, so I'll set up the algebra.
If it's F equals MA and A is equal to F over M, the F on top, is that tension minus cosine of 60? Like, could you set it up where we can literally?
Yes, I'll do that very quickly. Okay.
Belongs to.
So you know this
M
is
and the F is going to be the friction minus cosine of 60. That's what we're trying. Yeah.
Okay. Yep. This is equal to force friction equal to 1 newton. This is equal to this is this component. This left thing is this is the axis we're working on. This axis. This is the x component of this force, right? This is the x-axis of this force. So we know that this is 10 newtons. Again, we set up our triangle like that. Then we do cosine of 60. Oh, sorry, it's S cosine 60 equals x over 10. That's because this is x. If we're just calling it x, over 10 newtons, this hypotenuse adjacent. We found that we know that cosine of 60 is equal to 1/2. We simplify that. 1/2 is equal to x over 10. We solve what is x? Well, x is 5. So we know that x equals 5. So we know that the x component, so I'm going to redraw this. So we know the x component, this is the box. This is the guy pushing on it, pulling on it. So we know that the x component of this force is 5 newtons. We want to find out what the acceleration is. Obviously, if you're just pulling something along the floor, it's not accelerating up or down. So that means the F net in the y direction is 0 because it's not accelerating up or down. We know that because of F equals ma. If a equals 0, F has to be 0. However, it's accelerating to the left because he's pulling on it. In the direction he's pulling it, F is not equal to 0. That means A is not equal to 0. So we know that he's pulling on it with 5 newtons of force, but he's also being opposed by 1 newton of friction, right? So we want to find out what the total net force is in this xy plane, in this x plane, in this plane along this, right? So from here to here, we want to find out what the net force is in the x direction. Well, if it's going 5 this way and 1 this way, the result of these two together is just 4 in this way, right? So if you pull with 4 newtons and somebody opposes you with 1 newton, you're still in the end pulling with 4 newtons. So the total is 4 newtons. At the F net, the net force in the x direction is 4 newtons to the left, specifically to the left. So we can now use the formula F equals ma, Newton's second law, to find out what the acceleration is, because we know what the force is, it's 4 newtons. We know what the mass is. They told us in the problem it's 2 kilograms. Only unknown is now acceleration, which we're trying to find. Now we can just do simple math. 4 newtons divided by 2 kilograms is equal to 2 meters per second squared, which is the answer choice. Yes, mass is always in this situation, mass is always in kilograms. In physics, generally it's in kilograms. In chemistry, sometimes it's in grams. If it were in grams, you would convert it, yes. Because Newton's also takes into account the fact that it's in kilograms. So if it's physics, you would always just keep it in kilograms. If it's chemistry, you keep it in grams. Yeah, as Tim said in the chat, when you're dealing with newtons, you're dealing with kilograms.
Mark, I have a question. So, can you explain that unit again? How did you get to newtons and kilograms?
Right. Do you know what the unit of force is?
Newtons.
Right. You know that the force is 4 newtons because it's a force. You know that the equation that we're working with is F equals ma. F is force. Force has units of newtons, therefore 4 newtons. M is mass. Mass has units of kilograms, 2 kilograms, because they told us what the mass of the toy was. It's 2 kilograms. 2 kilograms. Acceleration, you know that acceleration has units meters per second squared. That's the only thing we have left. Acceleration, 2 meters per second squared is the answer. And that's what the answer choice is. Does that make sense? Or
how did you cancel that out to get meters per second? I'm just trying to figure that out. Like,
I see. Right, because newtons is not a standard unit. It's a unit of force. Newtons is and we can actually do this as an exercise to derive what the newtons is. Newtons is actually, and if you want to think about it, it's kilograms times meters squared. Oh, I'm sorry, meters per second squared. This is what newtons actually is. These are the standard units of newtons. Kilogram meters per second squared. This is what a newton is equal to a kilogram times a meter divided by a second squared. Does that make sense? We just simplify it down to newtons because we don't want to write this every time. Does that make sense?
yes, but how did you get to the final ending meters per second for acceleration?
Well, you know that the unit, what is the unit of acceleration?
Meters per second squared.
Well, that's how we know, because any acceleration, no matter in what situation, acceleration always has a unit of meters per second squared. Does that make sense?
Yes, I think so. Okay. Yeah.
Okay.
I have a question.
Please.
When it's asking for applied force, do we always know that that is the arrow that's pointing, like the diagonal arrow where you wrote 10N? Is that always what the applied force we should be looking for?
So, it depends. They'll try and label it as best they can. So if there's a string, they'll write T under the string. There'll be like a line and it'll say like T under it, and that's how you know it's a string. The reason you knew this was the applied force is because this was just the only arrow in the picture. So you kind of just assumed it was the applied force because they mentioned that there was an applied force and this is the only direction. But yeah, all forces are written as arrows. So like you saw, I drew, I drew this to represent gravity, this to represent friction, this to represent the normal force. But this arrow represents an applied force, right? It's just because it was the only other force it could be. It was the only force it could be. You know, it couldn't be normal force because normal force always perpendicular to the ground, gravity always down, friction always opposes movement. Does that make sense?
Yes, thank you.
No problem. Any other questions before we move on? Okay. So formula sheet. This is kind of like a summation of what we've already been talking about. So all forces, the general formula for forces is force equals mass times acceleration, F equals ma. For weight, Fw, force is equal to mg. Again, very similar to the basic equation, just using gravity as the acceleration. Normal force is F equals mg on a flat surface. It's also F equals mg cosine theta on an incline. So if we want to go back to our incline, I mentioned that this component is, well, it was W, but it's essentially just mg sine theta. So this component is mg cosine theta, right? And notice how on an incline, this box is not accelerating up or down. It's not accelerating at all on this axis, on this plane. And that means the net acceleration is 0. That means the net force is 0. That means whatever this component of weight is, the mg cosine theta, that means the normal force has to be equal to it, just in the opposite direction, right? Because they have to cancel out to make 0, right? So you know that if this is mg cosine theta, this also has to be mg cosine theta, just going in the opposite direction, right? That's how we figure out what the normal force is. On an incline, it's always just mg cosine theta, right? But there's no exact formula and it varies by situation. Like in this case, I actually incorrectly said at the beginning, normal force is equal to mg. It's not, because if you notice, mg is going down. This one has a y component of this is a y component of the applied force, right? Equal to 10, which is the applied force, times sine 60. So you actually, since it's not accelerating up or down, you have to add it together, this y component and Fn, and set them both together equal to mg. So in this case, mg is equal to Fn plus 10 sine theta, 10 sine theta, which in this case is 60, but 10 sine theta. So Fn, if you were to isolate it, is not equal to mg. It's equal to mg minus 10 sine theta. Does that make sense? Does that make, oh, I shouldn't delete that. There you go. Does that make sense to everybody? Normal force in this case is not mg, is not equal to mg, even though it is a flat surface, because there's another force here that's going up. These two forces combine equal mg.
So for mg, Mark, so that so the normal force is it's the same as when you're finding the sine of y over the hypotenuse of 10. Is that also equal to the normal force?
No, that's the applied force. No, because okay, so the normal force is just the ground pushing up. The applied force is, you said the child was dragging his toy, so like this 10 is equal to is just the child dragging it. So the 10 sine theta is just the kid, like the force the kid is using to drag it. Does that make sense? And if you want to think about it this way, right? When you're dragging something, especially at an angle, and you're kind of lifting it a little bit up, the ground isn't using as much effort. The ground isn't applying enough of a force to cancel out gravity because you're taking some of that burden onto yourself in order to drag it, in order to move it, right? Same thing if you're trying to like kind of like lift like something heavy, like the ground normally, if you're just not touching it, the ground has all of the weight on it. If you kind of like pull a little bit up on something, try and lift it a little bit, not enough to lift it off the ground, but just a little bit, the ground is not pushing up as much on the object because you're also pushing up, you're pulling up a little bit on the object. So the normal force is less than if you just left it alone. Same thing in this situation. The kid is kind of like lifting it a little bit. So the kid plus the normal force is equal to gravity instead of just the normal force being equal to gravity. Does that make sense?
A bit lost, but okay.
Is there anything like in particular that you
So how would I solve to find the value of the normal force?
Okay, I'll show you, sure. No problem. So I mentioned gravity, it's going down, normal force going straight up, and then there's also this going up, okay? This component. We know that this component is equal to 10 sine theta, right? This is equal to the normal force. This is equal to mg. Right? So do you understand that these, because there's two arrows going up and only one arrow going down, right? But the net, like when you add up all of the arrows together, they have to perfectly cancel out. So the two arrows together have to combined have the same value as the one arrow going down. Does that make sense?
So it's all of it is a net like force total. Is that what you're saying?
Net force is just the combination. A net force is always the combination of all of the arrows. It's just,
so that's what that is. It's the net. You're finding the net force to find the normal force. Oh,
well,
okay.
well, yes. No, wait, you're
Okay.
right, because the net force is zero. Do you know why the net force is zero?
Because the normal force is canceling out the weight, right? W equals mg.
Yes, but that's not why. Why is because you know the formula we just talked about, F equals ma. In this formula, F is equal to just net, it's F net, right? It's net force. If there's no acceleration, if A is equal to 0, that means no matter what m is, F net is always 0. We know that the box isn't accelerating up or down. We know that the acceleration of the box, because the box not moving up or down. Because of that, we know that A is 0. If the A is 0, that means the F net is also 0. Again, if we know that the A in up or down is 0, we know F net in up or down has to be 0. If we know F net is 0, that means we know all up arrows and all down arrows have to cancel each other out in order to make an F net. When you add all of the arrows together, it has to be 0. That's why we know that these two arrows are going up, this one is going down. Because we know that they have to cancel out, we know that the two up arrows have to add up to be the same as the one down arrow.
Because there's no acceleration.
Okay, yeah. Yes.
Right?
Yes. That's correct.
And that's because they didn't give that to you. Now, if they had given acceleration, that would be a different.
Yes, it would be a different story. Yes. All right.
But there's velocity. There's velocity. Well, there would be, right?
Sometimes there, again, acceleration. That's a more tricky subject, and that's more you have to do by a base. Just because I don't want to hold up the whole class, and we still have a lot more to get through. If you have any questions, please come to office hours. Please email me. But I have to move on because we still have a lot more to go. Okay, sorry. Anybody else, anything quickly? All right. So again, we mentioned normal force, spring force. Again, F equals kx. K is the spring constant. X is the distance that the spring is currently extended to, minus it's from the distance it is currently from its normal position. This is the normal position. This is the extended position. This spring can't compress, but if it could, you could also compress it. Friction is equal to mu times Fn. Mu is just the constant, and different surfaces again have different mu's, and mu is this like U looking letter. It's Greek. Again, so like ice would have a very, very low mu because there's no friction, whereas something like concrete has much higher mu, right? And depends on the surface you're having friction on. Mu, there's two different types. There's static and kinetic. Kinetic is when an object is already moving and it's usually lower. Static is when an object is at rest and you're trying to move an object that's at rest. It's usually higher. Tension, again, varies, no exact formula, just like normal force. Any questions on this before we move on? Any of the formulas, anything with force, before we move on to work and power? Sorry, I'm just checking the time and the clock's above me. Okay. Okay, let's move on to work and power. Work, okay, so work is a quantity which measures the amount of energy done by an action. If you want to think of it that way, it's very difficult to describe what work is. Work is a very, very complicated topic that the MCAT only very briefly covers. Work is just like, that's how engines like are made. That's how like refrigerators, everything works, but we're covering it very, very briefly for the MCAT. The main equation that you will have to know is work equals force times distance times cosine theta. The units of work is joules, which is the same unit as energy. So again, we know F is force, D is distance, and cosine theta, I'll explain in a second. So essentially, if you want to think about it this way, work is just force times distance. If you apply a certain force over a certain distance, that's how much work you do, right? Cosine theta refers to directions. Again, we talked about vectors. It's a difference in angle between the force you're applying and the work is being done. So if you're applying a force forward and then the work is being done like kind of at an angle, that's where cosine theta comes in. It's different, by the way, from the incline that we mentioned earlier. So like this alpha is not equals to theta, the 60 is different. It's a little bit different, but they'll give you a theta if they ever ask you for this. But most of the time, the difference in angle is 0 degrees, in which case when theta is 0, cosine theta is 1, and it just basically gets removed and it's just force times distance, okay? There's also the quantity power written as P, which is measured as work over time. Again, if you do a work over a certain time, you get power, that's the equation. The units of power are watts or joules per second. Watts is the standard. The simplified version, joules per second, is more of a kind of like fundamental, where it's like work is joules, time is seconds, joules over time. Okay. If you combine the two equations, you get power is equal to force times distance over time, because force times distance is equal to work. Right? Does that make sense? I'm very briefly covering these because work and power are not huge topics. Any questions? Okay. Yeah, and just to mention, like, work and power is very small topic on the MCAT, but if you have any specific questions, if you encounter any practice questions, please email me, come to office hours about work or anything like that. Now I want to get to more complicated force topics, starting with torque. So when you apply a force onto, like we were talking about, a block, you can move the block laterally, which means just side to side, up, down, whatever. More complicated situation is when you apply a force onto some kind of arm, lever, hinge, or anything that pivots. For example, on a door, you apply a force on a door, the door doesn't just move this way or like this way. The door, it rotates, it pivots, it opens or closes, right? Same thing with like your arm around your elbow. Your elbow is the pivot point. You apply force to your arm like this, the arm, it rotates, it pivots, right? This is called torque. Torque is you can think of it almost as like a scaled force that is being applied to a pivoting object. What I mean by scaled is that not all of the, in a sense, this is kind of like a not like textbook definition, but not all of the force is going straight into pushing the object, right? And the equation for this is torque equals force times distance. And I know it looks like a T, but it's actually not a T. It's the symbol is not a T, it's a tau. They just look very, very similar, but it's a Greek letter T. But tau is equal to force times distance. Distance measures the distance from the application of the force to the point of pivot. For example, like going back to my arm, the elbow I mentioned is the point of pivot. So if I apply a force here, it's a very short distance from the pivot point. If I apply force here, it's a longer distance to the pivot point, right? And that's what distance measures. If I go like maybe even further here on this side of the elbow, the distance is again short, okay? It's always from the pivot point. So for a door, it would be where the hinges are. For like a seesaw, it would be in the middle where it pivots around, okay? So again, the hinge on door, the middle of a seesaw, elbow on an arm, right? So the result of torque, like I mentioned, is not lateral movement like it normally is with a force. Like you don't, if you push like a door, it doesn't just like move forward, it rotates, right? It's rotational movement. Applying to an object either rotates it clockwise or counterclockwise rather than moving it laterally. The direction is something you may need to figure out based on the direction of the force and which side the hinge is being applied to. This is mostly just like kind of like logical, and you'll be able to figure out when you're given a diagram. If you apply force on like a door in this direction, it'll open up, it'll rotate this way. If you apply force in the opposite direction, it'll rotate the other way. If you were going on a seesaw, going this way would go rotate it this way. Applying a force upward would rotate it another way. Going on the other side of the seesaw would rotate it a different way, okay? It's something you have to figure out. Before we move on to the next poll question, you guys have any questions with how torque works? So I want to mention that before we move on, actually. So the closer you are, and you may like be familiar with this, the closer you are to the point of pivot and the closer the force you're applying to is the closer to the point of pivot, the less actual scaled force is being applied. This is where I was getting at with it before. So if you think about it like a door, if you apply force right where the hinge is, if you try and like push on a door right where the hinge of the door is, it's really hard to open a door. If you push a door all the way on the edge where the knob is, it's very easy because you're very far away from the point of pivot. If you're very close to the point of pivot, it's hard. You need to apply way more force in order to get the same torque. Whereas if you're far away, it's much easier. And you can see that in this equation too. If you have a very small distance from the point of pivot, the torque is going to be very small. Whereas if you apply a force far away from the pivot, even if it's a smaller force, the torque is still going to be really high just because of the distance, right? Again, with your arm, if you want to think about it, applying a force here, it's very hard to move your arm. Applying a force here, very easy to move your arm like this way and that way, rotate it. Okay, so pushing close to a point of pivot is very difficult, is what I'm getting at. Much more difficult than pushing it farther away. So let's get to this poll question. I'm gonna relaunch the polling. This is a little bit complicated, and you may need a pen and paper for this. If you see an angle here, just but notice that it says approximate, so you don't really have to know exactly about angles. Like there's 75 degrees. So just work on it. Take 3-4 minutes. I know this is a pretty difficult question, so please just try your best and we'll go over it and we'll go over it together. Okay, I'm gonna end the poll in a couple seconds. Last chance. Okay. The majority of people picked C, 46%, with the next highest being B, 31%, with a couple of you picking A and D. The correct answer is actually B, not C, and we'll go over it together, okay? So as you can see, this is, as I mentioned actually even earlier, the arm, especially around the elbow, is a pivot point. So you know this is a torque question, right? And with all torque questions, you know that there is, depends on distance, right? So let's look at force diagram, just like with all force problems and even torque problems. So there's a downward force of 10G, G as in the 9.8, right? Downward. And there's a force upwards, right? Along the bicep. And the bicep, you can think of it almost as a string or rope. So the force is actually a tension, right? Muscles are very similar to strings and ropes. So they would be using tension. Right, and we know that this is the point of pivot, the elbow. And we try and always use meters. So this 35 centimeters long is 0.35 centimeters away, or 35 meters, I should say, my bad. 0.35 meters away. This force is being applied 0.02 meters away, right? And it's applying an upward force. So,
I have a
yes, please.
is that 10 grams?
No, it's 10 times G. G as
Oh.
in 9, G is equal to 9.8. It's yeah. So it's normally it would be mg. We know the m is 10, G is 9.8. It's not grams, it's 9.8.
Oh, 10
sorry.
kilograms. Okay.
Yes,
And
G is, yeah, go ahead.
And is that dot where the 75 degrees is that the pivot point? Is that the elbow?
Yeah, this is the elbow. This is the elbow. This is the pivot point, right? Okay, so this is 0.02 meters away from the pivot point of the elbow. So you know, essentially, you want it to keep staying. So you want the F net to be 0, right? You know that you have a force coming here and a force pushing up here, right, by your bicep. You know that this force is equal to 98 newtons, right here. And then because of torque, the torque is actually, even before you even begin to think about torque, you know that it can't be D or C, because as I mentioned, going close to the point of pivot is very difficult, and you need to apply way more force in order to get the same torque as if you, rather than if you were doing it far away. Since the weight is at the end of your arm, it's very far away, so it has a very high torque. In order to get the same amount of torque, but just by pulling here, you would need way higher force because the distance is way smaller. You would need a way higher force than 98. So it would actually be like over 1,000, right? So you can already eliminate C and D, and it's get down to at least 2 answer choices. So if you were to, I guess, pretend for this that this angle didn't exist and it was just a straight line, then you would have T as the tension times 0.02 is equal to 98 times 0.35, right? You do this, then you'd multiply these out, and then you'd divide these by 0.02, right? And that's how you get the tension. So when you do that, and I'm not going to do the math right now, but just this is what you would do. And then once you do that, you'd get a tension, right? And the tension would be about like 2000, 1750, something like that. Well, you know, you can see that this is at an angle, right? It is a 75-degree angle. So then you have to think, okay, well, which component am I looking at? Well, you're looking at this top component, this one going up, right? This would be sine because it's opposite. It's right here. So it would be opposite from the angle over the hypotenuse, right? So it would actually be sine 75, right? Because it's opposite over hypotenuse, so it's sine. However, sine 75, you may not know what sine 75 is. I don't know what sine 75 is, but I know that it's very close to 1, right? Because you know that sine 90 is 1. Whereas sine of 60 is, I think, radical 3/2. It's very close to 1. Sine 75 is very close to 1. Essentially, you can almost consider it as there is no angle, as it is just a flat up. So you wouldn't, in order to get 3800, so the tension you would get if it was flat would be about, I think 1750, I believe, if I remember right when I calculated it. You'd need to like divide by 2. So you'd need a sine of 30 in order to get A as your answer. Sine 75 is nowhere near sine 30. It's much closer to sine 90, which is 1. So therefore, B is the only choice within that range. It's the only choice close. Okay, now I'm going to look at the answer choices. Okay, so how did I, first question, how did you get 98? So we know that this is a mass, right? In order to get a force, you would multiply m times g, right? The mass is 10, g is 9.8 meters per second squared. G is the gravity constant, 9.8. 9.8 times 10 is 98. Like Tim said, you can often round it to 10. Just in this case, because you're already multiplying by 10, it's very similar. It won't matter. Yeah, and it doesn't matter what the, yeah. So sine of 60, Opal, I'm confused. Are you saying sine of 60 is 0.86, 0.866?
Yes, I think because you were trying to estimate what is sine of 75, and since we already know certain signs, right? We memorize that the 60 is 0.8, and we know the sine of 90 is 1. So we know it has to fall between 0.8 and 1. So you're right. You did estimate.
Exactly. Yes.
One.
Yes.
So that's how I figured, you know, since I didn't know the sine of 75, but I did know the sine of 90 and the sine of 60. So I've said it had to fall between 0.8 and 1. Is that a rational?
Yeah, that's exactly right. And that's exactly what you were expected. Nobody's really expected to know what sine 75 is. They just expect you to know, like, that's why they gave you the answers so far away in range, or why I gave answers that were so far away in range, because it would be enough for like you to like basically guess, especially they say approximate. How did I choose between sine and cosine? Okay, so we're looking for the upward component. We don't care about the x and y component in these two directions, right? We only care about the up and down right now in this case. The up and down is right here, this line, right? This side of the triangle, right? So we can make our things. We know the angle is 75, and we know we're looking for, we'll call it y. We'll call this, whatever this is, y. We're looking for y over t. Well, what is y over t? Well, this is the opposite angle because the angle's right here. This is opposite. This is hypotenuse. Opposite over hypotenuse. So SOHCAHTOA, SOH is sine. So you do sine 75 rather than cosine 75. If you're looking instead for this side, which is the adjacent or the x component, then you would use cosine 75. But in this case, you're using sine. Does that make it clear? Okay, so in about the T is, oh, the T is tension. I'm sorry. Yeah, it's a little bit confusing, but the T is tension because the bicep is like I mentioned, the bicep is basically like a string or a rope. All muscles are, so we use tension. And we divided both sides by 0.2. So because we're trying to isolate tension, that's what we're trying to find. So we want to set if the arm is not moving, that means F net is 0. That means you want to set the up equal to the down. The down we know is 9.8 times 0.35 because it's torque. So this is the torque of the going down of the weight at this end. And this T times 0.2 is the torque of the bicep, right? And we set them equal to each other if we want to isolate the torque. If we want to isolate the tension, we divide both sides by 0.02, okay? So we do this force times the distance to get the torque, and then we divide that by the distance of this to isolate this force.
Mark,
Yes.
could you rewrite that again, like to
Which part?
to solve that variable for T, because I'm pretty sure a lot of people are still trying to figure out how did you, yeah, thank you.
No problem. Okay, this is going down. So again, we know this is a torque problem. Torque, this is, I'll write my taus like this, if it makes it easier, okay? Oh, that looks kind of wrong. I'll write my taus like this. This is tau, this is T. Okay, tau is equal to force times distance, okay? We know that the tau of this, the torque of this is equal to the force, which is mg times 0.35, because that's how far away it is from the point of pivot, which is the elbow, right? We know, and we'll call this weight, the tau of the weight. This is the weight. Then we also have the tau of the bicep going up. That's equal to T, which is the tension of the bicep, which is the force exerted by the bicep, times 0.02. We know that because one is going down and one is going up, and the elbow itself, the arm itself, is not moving up or down, it's not rotating. So that means the net torque, just like with the net force before, the net torque is equal to 0. If the net torque is equal to 0, we know that TW and tau W and tau B are equal. Therefore, we can set it like this: mg times 0.35 is equal to T times 0.02, right? We want to find out what T is, so we want to isolate T. We know what M is, we know what G is, we know that 0.35 is on this side. So in order to isolate T, we would just simply divide both sides by 0.02. And then this together is what T, tension, is equal to. Does that make sense? Why did I not subtract from the entire level arm? Because this is not the point of pivot. This is the point of pivot. They told us that this was 0.35 away from the pivot point, and they told us that this was 0.02 away from the pivot. All we care about is this relative to the pivot, not from each other, not from anything else, just from the point of pivot. The point of pivot is the elbow, and that's okay. Yeah. Anything else? Any other questions before I continue?
And the T, you're finding the sine.
Go ahead, sorry.
You're finding for the T you're finding, but how can you find that if they didn't give you the value for the opposite?
I'm not sure what you mean by the opposite.
So like the sine of 75 opposite over hypotenuse in
Right.
order to find what t is.
As people are doing fireworks outside. Sorry about that.
Did they give you that?
So they gave us what the angle was, 75. Technically, so and we're looking for only for the up component, right? The up
Yeah.
component is always this side. So we'll call it y. The up component is y, and it's this right here, from here to here.
But that would be y over t. But since there's two unknowns, how
Well,
did you?
So we actually we can find that out because we know that sine of 75 is equal to y over t. And then we can actually substitute in two. Do you know the phrase one variable, one equation, one unknown, one equation, you can solve it, two unknowns, two equations, you can solve it, three unknowns, three equations, you can solve it. We have two unknowns, two equations. So you're right, we don't know what y is, but we actually do know what t is equal to. T, we just said it right here, t is equal to mg times 0.35 divided by 0.2, right? You just substitute this in here for t. And then you multiply that, and then if you want to just isolate y, you just bring that over to this side. In this case, though, however, we know that sine 75 is almost 1. It's practically equal to 1, right? So we know that y is practically equal to t. What we're actually looking for is not t. We're actually looking for y. But because we know that sine 75 is practically equal to 1, y is practically equal to t, and we know that if we find t, we practically know what y is. Does that make sense?
Yes, but that was a little bit. Yeah, I get it. But that was.
And somebody asked, there is one more topic we'll be covering today. It's centripetal force. So if you guys already have a clear understanding of centripetal force, you can go. But that on top left is, I believe, centripetal force. Let me just double check actually before I say that and we miss something. Centripetal force, and then and gravitational force. So centripetal and gravitational force are the only things left. Gravitational force in big G mm over r squared, if you guys know what that is. So yeah. I'm sorry that this went so long. It was just because there are a lot of questions and I tried to go in depth with all of them, but yeah. Can we move on from this clicker question, or do you guys want to spend some more time on it? Move on? Okay, let's go forward. All right, centripetal force. So another common force you may encounter that we have not yet talked about is the centripetal force. Centripetal force is always present whenever you have anything spinning in a circle. So say if you took a string with a ball on it and then you just spun it in a circle, centripetal force. If you had a car moving in like a circle to make like a donut, centripetal force. If you have a planet orbiting the sun, centripetal force. Everything has anything moving in a circle has a centripetal force, right? Unlike the forces we've already talked about, like friction or tension, centripetal force is a net force. So we've actually talked about net forces before, like we mentioned in, I believe, one of the old slides. If we want to talk about this slide, the net force up and down combined was 0. F net in the y direction was 0, right? But F net wasn't an individual force. It was a combination of different forces. Well, that's what the centripetal force is. It's a combination of different forces that we just gave it a name. It's called a centripetal force, okay? So like we had here, F net was 0. It's a combination of total force. Centripetal force is a combination of different forces that we just gave a special name, okay? When you're moving in a circle. What it means is there's always a centripetal, so there's always a centripetal force, and it always points in the middle of the circle. So if you think of the planet orbiting the sun, the centripetal force always points towards the sun. Doesn't matter if the Earth is here, it always points this way. It points this way towards the sun. If the Earth is here, it points down towards the sun. If it's here, it points left towards the sun. No matter where it is, it always points towards the middle of the circle. Okay, and same thing with the centripetal acceleration. If you have a force pointing inwards, that means F equals ma. You also have an acceleration going inwards. Okay, so and a car going in a circle is always accelerating inward. A planet orbiting the sun always accelerating inward towards the sun, if you want to think about it that way. And it's made up of different forces that we've already talked about: tension, gravity, spring force, anything. The exact composition of forces depends. For example, with a planet orbiting the sun, most of the force is gravitational force. So most of the inward forces are due to gravitational force. If you have a ball spinning on a string, most of the force is tension from the string. It depends, right? But the key thing is centripetal force is a net force, okay? The way like I mentioned, centripetal force always points in the direction of the epicenter of the circle. Its magnitude is always equal to mass times velocity squared over r, mv squared over r. That's what centripetal force always equals to. And unlike where I said make a force diagram, with centripetal force, like I mentioned, it's a net force. You can always just find it using this formula. Sorry. The acceleration of an object also always points to the center, like I mentioned, and it's defined by this formula. Acceleration, centripetal acceleration is equal to v squared over r. If you can actually derive this from, again, classic formula, F equals ma. If the centripetal acceleration is v squared over r, in order to get centripetal force, you just multiply this by m, and voila, we have mv squared over r. Very easy. Okay, and that's how you always find centripetal acceleration, centripetal force. Velocity is instantaneous velocity, and this is where I was talking about the difference between instantaneous and average velocity. At different points in the rotation, the object will have different instantaneous velocities. So for example, if you're planet orbiting the sun, the planet is always orbiting the sun has a velocity, if it's at the bottom and it's going in a circle like this, right? When it's right here, it has instantaneous velocity going in this direction, exactly to the right. And then it has like this. It always follows the circle. The velocity always follows the circle, whereas the acceleration always points upward, right? And if you're having a question like this, they'll give you the instantaneous velocity. They'll give you the radius of the orbit, right? The r is the radius of the orbit. And they'll give you the mass of the object, right? It's the mass of the object that's orbiting, right? And F equals the force. This question, I don't want to spend too much time on it because we're already going over, so I'm just going to skip this question. Motorcycle, and I'll go over it together. Motorcycle moves around a curve of radius r with speed v. Later, the cycler increases the speed to 4v and drives around a larger radius of 4r. By what factor does centripetal force on the cycler change? The answer is 4. And we can see because, so we know that F equals mv squared over r. And we'll call this F1 initially, and we'll call F2 after a certain time. We'll say V1, R1, V2, and R2, right? We know that V2 is 4 times V1 and R2 is 4 times R1. So we can actually substitute it like this, 4 times R1, and this is V1, 4 times V1, right? Now, let's simplify it. Now, this cancels, this cancels. Okay. So now let's track it. So we put the 4, so the velocity is 4 times what it originally was, and the radius is 4 times what it originally was. Because the velocity is 4 times, but you square it, so it's actually 16 times. So the squared is actually 16 times more, right? Rather, where this is only 4 times more. Again, 16 and 4 cancel out, and you're left with 4 mv squared over r compared to mv squared over r. That means it's 4 times greater, right? And you can figure this out easy just because you know there's a squared at the top, no squared at the bottom. So if you increase by the same factor, the top will always increase by more just because it's squared. Does that make sense, or do you guys want me to go over it? Any questions? Anything? Okay. Last step is gravitational force. So the final non-electromagnetic force you may see in the MCAT is the gravitational force. We've already discussed the effect of gravity on us by the Earth, but any two bodies that have a mass always have a gravitational force towards each other, right? And if we're talking about direction, it's always towards the object. If I'm standing here and I have a water bottle right here, my gravitational force is always going like from mine's towards the water bottle is going towards the water bottle is going towards me, right? The gravitational forces are always towards each other, right? And we do have a gravitational force, even though you don't think of it that way. We always do. It's just extremely, extremely, extremely small, just because we're not massive. We're like very small, and we'll see why that is in a second. The gravitational force is so small in most cases. The only time it actually becomes relevant is when you have two objects with very high masses. So such as planets, moons, stars, something like that. Even like big animals like whales wouldn't have a gravitational pulse or force because they're just very, very small compared to a planet, right? We'll talk about why that is. Look, the formula for gravitational force is big G times m1 times m2 over r squared. Big G is a constant and it has a fixed value. M1 is the mass of object 1, M2 is the mass of object 2, and r squared is radius squared. Radius squared is the distance between the two objects, but it always goes from the center of mass of the two objects. So for example, the center of mass of the Earth is the center of the Earth. So it's always the distance from the center of the Earth to whatever other object it is. And that's one of the reasons why for us it's 9.8. Because when it's 9.8, it would change when you're going on a different altitude, but the center of the Earth is so far away from us that even if you were to go like 20 feet, 30 feet, 40 feet, 100 feet into the air, the difference would be like very insignificant from where we are now, how far away we are from the center of the Earth, right? So that's why the gravitational, the little g, acceleration due to gravity is always 9.8 for us. Technically, it always changes depending on altitude, but by such a small amount. Big G is, I mentioned, a constant. Value 6.67 times 10 to the negative 11. I would recommend memorizing it, but they might give it to you on a test, so up to you. I would still recommend memorizing it just in case they don't. The units are newtons times meters squared over kilograms squared. Again, you can figure this out. This is kilograms, so you have 2 kilograms in the numerator, means you have to have 2 kilograms in the denominator. Radius is distance, so distance squared, 2 distances in the denominator, 2 distance in the numerator. This cancels out with the radius squared, this cancels out with the 2 m's. All you're left with is newtons, which is equal to force on the left side. Units on the left equal units on the right. Again, because big G is so small, if you calculated this using my mass and this water bottle's mass, the resulting force would be like 10 to the negative 100, or 10 to the negative probably 10, 11 units, newtons, which is so small compared to like this has like a gravitational force from the Earth of probably like 10 newtons, right? Somewhere around there. 10 newtons versus 1 times 10 to the negative 10 newtons, big difference. So the only time that gravitational force really matters is when the two objects are massive, okay? And yeah, does anybody have any questions about this? How to calculate gravitational force, centripetal force, anything like that? Anything we've covered in this lecture so far? And so this is the end. I actually have to change this slide because this is old. Office hours are not Saturdays at 12 to 2 p.m. Sorry, this was a mistake. We will try and get the PowerPoint recording out to you. If you don't find them, please email me at this email. I'll send them to you. But thank you very much for joining us. Sorry it took so long. Yeah, it was just because we had a lot of questions. And I tried to kind of go in detail, and this was a big topic. For the next lectures, I will try and make it a lot shorter, a lot more concise. Yeah, as mentioned, all lectures will be Thursday, Friday, and Saturday at 8:30 to 8:30 to about 10:30. So please join us tomorrow, join us Saturday if you have. Look at the schedule on the GroupMe, join the GroupMe if you haven't already. There you'll find all the updates. The schedule is there as well, the spreadsheet, to see what topics are going to be covered.
Awesome. Thank you, Mark. And I know it was long, but the questions were really good. Some that I had as well. So even you spending time on them helped me as well, even if I didn't say it. So do appreciate it. Thanks.
No problem. Yep. And if you guys have any questions, please stick around. I'll be here for maybe another 5-10 minutes answering questions if anybody has.
Yeah, Mark, I have a question on the torque. So if you had a ladder and you had a fat person weighing heavy and he's at the end of the ladder, where would you need to put a lighter person to balance it, closer or farther?
So in a ladder, with ladders, it's a little bit complicated because ladders are usually like this. The point of pivot, so I'm assuming the ladder is like kind of like strapped to the floor or like nailed to the floor somehow, so it doesn't like, otherwise it would just like move like this, like it would like fall, right? But if it's like to the floor, it's bolted down, like, or like a pole or like a ladder or anything like that. If you had a fatter person, say here, like in the middle, in order to balance it, you would actually need a lighter person, and I don't think this is possible, to either stand farther away, for sure farther away, but on the opposite side, in a way, like on the other side of the ladder, and like pushing it that way, but it's not really possible with the ladder. If we're talking about a seesaw, which is more like this, if you had a fat person here, like towards the center of the point of pivot, they would have a very small d, a small distance to the center, right? So the torque would be small. You would put a lighter person in order to balance it on like farther away on one of the edges, right? Essentially, if you want a high torque, you want to increase the distance from the pivot point. Generally, if you increase the distance from the pivot point, you'll get a higher torque and you'll need less force. And you'll get more like scaled force, like I mentioned. Okay, well, if there's no other questions, we can end for today. And yeah, so we'll see you guys hopefully tomorrow. Have a great day.
Thanks.
Thanks, everyone. Have a good one. Bye.
Have a good one.